Good morning. Yesterday we saw how to draw a Lewis dot structures. While drawing Lewis dot structures, we consider electron as dots, as a particles. We given a dot for each electrons. Although electrons can also be a wave that you will be studying in quantum mechanics. So we are going to see further about Lewis dot structures. One of the concepts is the resonance structures. What is resonance structures? If you take a molecule, for example, ozone, O3, it is a allotrope of O2, which is present. O3 is present in atmosphere, very small quantity, but it is present higher atmosphere, in more quantity it is doing good thing for us, but in lower atmosphere it is doing bad thing for us. Apart from that, we are going to see what is the structure, what is the actual structure of O3. So you can write a Lewis dot structure for this molecule. So as usual, you have to find out what is the total number of valence electron first. So the valence electron equal to 3 into the number of valence electron for each oxygen atom, which is equal to 6. So that is equal to 18. So 18 is the valence electron. So you then next step is the choosing the central atom. So here, so the only one type of atom is there. The central atom must be the oxygen itself. So O, arrange the atom first around that central atom and then draw a single bond. Then that is drawing 2 single bonds consumes 4 electrons. So you have to subtract that 4 electron from the total valence electrons. So minus 4 equal to remaining 14 electrons. These 14 electrons should be distributed among these 3 atoms in such a way that each atom attains 8 electrons. So let us see this way, this way, this way, and then this way, this way, this way. So far we consumed 12 electrons. Remaining 2 electrons can be added to the central atom, because the terminal atom, these 2 are terminal atom which already now assigned, okay, we as we assigned attains 8 electrons. So the remaining 2 more electrons can be given to the central atom. Okay. Now see the total number of valence electron that was given to the structure, and that should match with the valence electron counted before. So here there are 3 lone pairs, that 6 electron, 3 lone pairs, 6 electron, 1 lone pair. So that means 12 plus 6 plus 6, 12 plus 2, 14, and then 2 bonding electrons. So 14. So that is 16, this is 18. So total number is 18 is coming all right. So the number of valence electrons are given to that, and it is matching with the what was counted before. Now if you look at that, whether all the atoms attained octet or not, it is not. Only the terminal atoms attain octet, that is 8 number of electrons are around that terminal atom. Now if you look at the central atom, it has only 6 electrons. Here 2, here is 2, here is the 2. So 6 electrons. Then what you can do is you convert the lone pair on the lying on the adjacent atom towards that central atom. So that you can do by drawing like this. So you can write O, double bond, O, and then single bond, single bond. So since you since there a pair of electron was pulled towards this oxygen atom, then it is left with only remaining 2 more pair of electrons, that you can draw like this. Okay, and then retain this lone pair here and retain these 3 lone pairs as such. Now if you count the number of electron around the central atom, it is 8, because 2, 2, 2, 2, 8. Now about this one 8, about this one is 8. So this is so this is the actual Lewis structure. So now the Lewis structure is drawn. This is Lewis structures, Lewis dot structure. You can call that as a dot structure or Lewis structures. Lewis structures. Now the same way what I did pulled one lone pair of electron from the atom lying on the left side. You can also do the same way for the from the right side atom. So, you can also pull this lone pair of electron and convert it into a double bond. Then you can draw a structure of this type, that is O, and then double bond O, two lone pair, okay, and then here it is 3, because you pulled only this one and this remain, these two remain same, and there is 7. Now, you can see the number of electron around the each oxygen atom, it is 8, here is 8, here again it is 8. So, now if you look at it, these two structures, that is structure, for example, this is structure A, this is structure B, both structures are equivalent, because they are correct Lewis structures. However, the question is, what is the actual structure for O3? That is a question to be addressed. So, these two structures differ only in the allocation of the electrons. That means, so on right side you give more electron for one structure, for another structure you give more electron to the right side or on the right side, then accordingly the bond pattern will change. So, these two structures differ only in the allocation of electron. It can be 1 electron or 2 electron, but they differ accordingly. When the allocation of electron is changed, the bond pattern will change, but they are Lewis structures. So, these two structures, now I am going to call this as resonance structures. Okay. These two structures are correct Lewis structures, but actual structure is not this one. So, these two structures are called resonance structures, which can be represented by this type of double pointed arrows. Double pointed arrow or double headed arrows, you can call it that. So, these two structures are equivalent and which differ only in the allocation of the number of electrons. So, which are represented, which are connected to each other by this type of arrow, that is called double headed or double pointed arrows. So, now the question is, okay, which is the actual structure, whether this is the correct structure for that O3 or this is the correct structure. Actually, none of them is the correct structure, which is surprising. Then what is actual structure? We have to ask that question. The actual structure is a blended structure of these two structures. Structure A and B are mixed to give a resonance hybrid structure. So, okay. So, the blended structure can be written like this. Like that. Now, you can see that, okay, the blended structure represents a dotted line. So, 3 oxygen atom, a single bond, and then you have a dotted line. That dotted line indicates that a partial bond. So, okay, partial bond. So, this structure is called resonance hybrid structure. This structure can also be called, these two, okay, these two structures, that structure A and B can also be called canonical structures. That means, these are the structures which are, structures which are imaginary structures. Okay. So, we imagine one structure to understand the actual structure. So, it is not the structure, it is existing. So, it is important to keep in mind that none of the structure never existed in reality. At any time, the ozone has either this structure or this structure. Its actual structure is a resonance hybrid of these two structures. It is a blended structure of these two structures. Because, so the concept here is the resonance or canonical structure, because if you draw one Lewis structure, it is not correctly telling the actual structure of the actual electronic state of the actual ground state electronic state of the O3. But if you combine these two structures, you could get a hybrid structure, which is called, okay, which tells which gives better explanation about the experimentally observed bond distances. If you go by these structures, you will see that okay, if you go by this structure, there must be a double bond and here there is a single bond. Okay. So, double bond distance are shorter compared to a single bond distance. So, experimentally what was observed is for O3, the OO distance equal to 128 picometer. If you consider actual typical OO bond distance equal to 148 picometer, typical OO double bond distance equal to 121 picometer. Now, the experimentally observed OO bond distance in O3 is 128 picometer, which lies between these two values. So, that means it is not a single bond, it is not a double bond, it is in between. Okay. So, the bond order is the concept we will see later on. So, the bond order is 1 and half. So, you can see here it is the bond order is 1.5, the bond order is 1.5. That is why its distance, OO distance is 128 picometer. It is not single bond or a double bond. Now, one more thing is that what I drawn for O3 is a linear structure. Okay. These two structures are correct as far as Lewis dot structure is concerned, but actual structure of O3 is not a linear, it is a bend. Actually, it is a bend O like that, its structure is like that. Now, so actual structure you cannot get, actual geometry of a molecule you cannot get by drawing a Lewis dot structure. It gives only how, what is the link, where is the lone pair located and what is the pattern you can get, but you cannot get what is the geometry of that molecule. For example, if you take for another example is the BF4 minus, you can calculate the number of valence electron and then you can do the Lewis dot structure and it will come out like this. And then you have to put the overall charge. This means overall charge of the species. Now, you can see that what I drawn here is a planar molecule. Actual structure of this tetrafluoroborate is a tetrahedral. It is a planar structure. So, this is actually a tetrahedral geometry. So, Lewis structure does not give what is the actual structure. It gives information about how atoms are linked, where are the lone pairs and or in other words is a bonding pattern you can get. So, resonance structures we can also see with more examples. For example, what is a Lewis dot structure for NO3 minus? NO3 minus, as usual you can calculate number of valence electron N plus 3 O, okay, 3 into O plus minus 1. For minus 1 you have to add 1 electrons. So, that is one has to keep in mind whenever there is a positive charge on a species, that means 1 electron is less. Okay. Whenever there is a negative charge, 1 electron is more, which is to be added to the actual valence electron. So, NO3 minus, okay, minus means 1 electron, that is to be added to the total valence electron count. So, as usual the valence electron of nitrogen is 5 plus 3 into valence electron of oxygen is 6 plus 1. Okay. So, that comes what is that 21, so 18, 19, so 24 electrons. So, 24 valence electrons came out. That can be arranged around this nitrogen molecule NO3 minus. So, then you can draw a structure as usual N O O O like that. So, there are 6 electrons are consumed to write 3 single bonds. So, 6 minus 6 it gives, so 18 valence electrons. That 18 electrons can be distributed around the terminal atoms, then you will see like that, like that. Now, there are 6, 6, 6, 18. So, 18 electrons are over, and then you have to give the overall charge. Now, if you look at the central atom, that is nitrogen atom, it has not attained the octet. Then what you have to do is, you have to convert the lone pair into a double bond. So, you pull this lone pair here and then see nitrogen O, okay, double bond here, here O. Okay. So, after pulling one lone pair, it has only remaining 2 lone pairs. Here nothing happened as such, here again. Then you have to put the overall charge minus. Same way you can write, okay, you can also pull this lone pair and you can write another structure. Like that, the overall charge is negative. Same way you can also pull this lone pair to give the nitrogen atom octet of electrons. And then overall charge is negative. So, now you can see that, okay, there are 3 structures can be written, okay, for a NO3 minus. So, that means these 3 structures are called resonance structures, which can be represented by a double pointed arrows. They are resonance structure. The resonance hybrid structure is this one. Which are shown as a dotted line, and the overall charge is negative. So, you can see that the double bond can be here or here or here, or if you take this one, okay, double bond can be here, it can be here. That means, all 3 structures are equivalent and they are contributing to the actual ground state electronic state of NO3 minus. So, that is why these structures are resonance structure or canonical structure or imaginary structure, you can say that, because we designed the structure to understand the actual structure. So, that is why it is imaginary structures, but you have to keep in mind that it never existed at any time for NO3 minus, but it is used to understand the actual electronic structure. For that purpose only, if you go for a quantum mechanics that we may be seeing later on, that actual structure of that NO3 minus is a combination of this structure, this wave function of this structure, wave function of this structure and wave function of this structure, and then you will get net wave function, and its energy will be lower compared to the contributing structure. So, these structures also called as a contributing structure. How much they contribute, that depends on the actual structure. It is not necessary that all resonance structures should contribute equally. Some may be contributing more, some can be contributing less, but they are contributing to some extent to the actual structure. So, depending upon that, one can find out from the quantum mechanics. So, these are all contributing structure to the actual structure, which is used to understand the actual electronic ground state structure. Now, as a result, the bond distance are average. You see, in the blended structure, the bond distance are average. It is not a double bond or it is not a single bond, it is in between, that we saw before, same way. So, another important thing is that if you take this molecule or any one of these, okay, now you have to give a formal charges. Now, we are going to assign formal charges. How to assign a formal charges? Formal charge Fc equal to number of valence electrons minus number of electrons in unshared pair minus number of electrons in bonding pairs. Divided by 2, which is very important. So, you first take here what is the, find out what is the valence electron of the atom. Suppose you want to assign what is the charge, formal charge for an atom, then you should first take up the valence electron. We are all concerned about valence electron because it is those electrons are involved in reactions. Rearrangement of those valence electrons are responsible for reactions. So, its reactivity is we are more or mostly concerned about valence electron. We are not concerned about inner core electrons which are intact, which are lying inside, they are not involved. But we are concerned about the valence electron because which are responsible for forming new bonds or cleavage of the bonds. So, you take a valence electron, you from that you subtract number of electrons present in lone pairs, or that is called unshared pairs. Okay. Suppose your lone pair is the number of electrons is 2, not 1. Okay. So, that is why the number of electron in unshared pairs minus number of electron in bonding pairs. Okay. There is a bonding pair, that means each bond is consisting of 2 electrons. So, that you have to, then that 2 electrons should be divided by 2. Suppose number of bond is 2, then the number of electron for calculating formal charge is 1. Okay. Number of bonds is 3, then 3 into 2 equal to 6, 6 divided by 2 gives 3. So, that value will be here, this value will be 3, like that. So, that will become very clear when you see a actual structures, actual calculation for formal charges. Now, this type of formal charge calculations are applicable only if the bonds are pure covalent bond. Okay. Covalent bond means a share of electron is, a pair of electron is shared between 2 atoms and they are equally distributed. Okay. And the assigned lone pairs are located on that particular atom only. Okay. So, these conditions should be there to calculate formal charges. So, now let us see few examples how to do a formal charges. If you take ammonium cation like that. Now, hydrogen has 2 electron because around this hydrogen atom only 2 electrons, which is that hydrogen is satisfied with the 2 electron because it has only the capacity of accommodating only 2 electrons. So, but nitrogen, around nitrogen there are 8 electrons, correct, 1, 2, 3, 4. So, 4 into 2, 8 electrons are correct. Now, the charge, what is the charge? So, the overall charge ammonium cation is plus. So, where is the charge, whether it is a hydrogen atom or at the nitrogen atom, that we can calculate. If we calculate formal charge for the nitrogen, how to come, we can find out that for nitrogen. Okay. Then the number of valence electron for nitrogen is 5 minus this minus number of electrons in unshared pairs. There is no lone pair electron or unshared pair of electrons on this nitrogen atom. So, it is 0 here, minus this minus number of electron in bonding pairs divided by 2. So, around nitrogen there are 4 bonds. Okay. So, there are 4 bonding pairs are there. So, 4 bonding pairs means 4 into 2 8, 8 divided by 2 equal to 4. Okay. That comes out to be plus 1. So, that is why charge on the nitrogen is plus 1. I hope this is clear how to calculate. This type of calculating the formal charges is very important when you write mechanism for organic reactions. Okay. Otherwise, you will end up with wrong, maybe thinking that wrong nucleophile attacking electrophile, instead of saying this atom as a nucleophile, you will say that as a electrophile. Like that confusion will come if you have not written the actual Lewis structures with formal charges. Now, so let us see for NO3 minus. There we found the overall charge is minus, but if you look at any one of the Lewis dot structures, for example, here. Now here there are 2 electrons, here there are 2 electrons, there are 3 lone pairs here on this. This is the overall charge is minus. How overall charge is came out to be a -1, that we can find out. So the overall formal charge is a summation, is a sum of the formal charges on each atom. So if you do formal charge calculation for each atom, then you will see that what is the formal charge, overall formal charge for that species. Now for nitrogen, if you do calculation, nitrogen is valence is 5 minus number of lone pairs on the nitrogen atom, number of electron in the lone pairs, there is no lone pair. So that means you can give 0. Then the number of bonding electrons, here there are 4 bonds, 1, 2, 3, 4. Okay, so 4 bonds, that is 8 by 4 equal to, that is 4. Sorry, here it should be minus. Okay, because minus minus. So valence electron minus number of electron in unshared electrons minus number of bonding electron divided by 2. So there are 4 bonds, that means 8 electron divided by 2 equal to 4. So that gives charge of +1. Sorry, +1, that is correct. So it is a charge of +1. Okay. Now let us do a calculation for this one. The valence electron for oxygen atom is 6. Okay, minus lone pair of number of electron in lone pairs. There are 3 lone pairs. So 1, 2, 3, 4, 5, 6. 6. Then number of electrons in bonding divided by 2. Only one bond is there between these two atoms. So by 2 equal to, okay, 1. Okay, -1. So that is equal to, this 6 is equal to -1. Okay. Similarly, if you do a calculation for this oxygen atom, it is 6 minus a lone pair of electron 1, 2, 3, 4. 4 minus number of bonding electrons, these are 2 bonds, 4 electron by 2, 2. Okay. It is equal to 0. Now if you do calculation, this is same as this atom, so you can right away assign -1. Now you can see that here is the minus, so here is the 0 formal charge, here is the -1, here is -1. Okay, you add them, -1 plus -1, okay, and then plus 0 here plus +1. Okay, -1, -1, 0, then +1. So you can see that -1 plus 1, then you end up with -1 only. So that's why we are putting -1. Is it clear? So we saw what is formal charge. Now let us see another example, and which is a little bit difficult one. What about N2O? You can calculate the valence electron 2 into N plus O, that is 2 into 5 plus 6. Okay. So 10 plus 6, 16 valence electrons. Now you can find out the central atom. Here the least electronegative or the atom with more bonding capacity. Bonding capacity refers to the presence of number of unpaired electrons. Okay, that is a bonding capacity. So nitrogen is the central atom, because there are anyhow 2 nitrogen atoms are there. You can write nitrogen, nitrogen, O. So there must be one single bond for connecting or linked to the central atom. So 4 electrons are gone, -4 equal to 12 valence electron. That 12 valence electron you can assign around this terminal atoms here and here, 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 here. Okay. So now the count the number of valence electron around this. Okay. So the 6 plus 6, 12 plus 12, okay, 12, 14, 16, that is the valence electron calculated before. It is matching with that one. But if you look at the number of electron around this nitrogen atom is 8. Similarly, around this oxygen atom is 8. So it is okay. But if you look at the number of electron around this nitrogen, it is only 4, that is 2 here, 2 here. So, only 4 electrons are, that is not obeying, which is as of now it is not obeying the Lewis octet rule. So, what you have to do is you have to pull this lone pair here, and then you can write resonance another structure, and then see whether it is whether it has 8 electrons. Like that. Now, you see here there is no problem with this nitrogen, there is no problem with this nitrogen because there are 8 electron, but around this nitrogen atom only 6 electron, because 2 plus 2 plus 2 6 electron, that means it requires 2 more electron from somehow from adjacent atom, so that it will be happy. So, what you have to do is you take away, you pull this lone pair to this one, and then you can have like this. Now, you can see that around this oxygen atom 8 electron, around this nitrogen atom 8 electron, around this nitrogen atom 8 electron. So, this is actual Lewis structure, this is a Lewis structure. When the central atom is attained the octet, then writing the Lewis dot structure is over. Now, you can see that this structure. Now, there are other way you can write the same structure. Let us write this one N here, like this. Now, you can also pull electrons towards this oxygen atom. So, you pull electron here, okay, and then this here, then you can write this structure like this, which I am going to call this as a resonance structure. Okay, after taking away one lone pair from this nitrogen atom, there is only one lone pair on this, and then it becomes triple bond, then nitrogen, then it becomes single bond, because this lone pair is changed to a this bonding electron pair is changed to a lone pair, like that. Now, still if you look at the structure of number of electrons shared by each atom is 8. So, here there are 8 electrons, 2 here, 2, 2, 2, 8. If you look at this nitrogen atom, there are 3 bonds, here 1 bond, so 8. Here 3 lone pairs, 1 bonding pair, so 8. So, this structure is also a correct structure, correct Lewis dot structure. You can also pull the lone pair of electron in the opposite direction. You can pull this here, okay, and then convert this bonding pair into a lone pair. Then you can see that another structure this way also. You can write nitrogen 3 lone pair, okay, it becomes single bond, and then nitrogen, and then it becomes triple bond, okay, and then you are left with a lone pair. So, from this structure what we did is taken away the lone pair from this oxygen, then it becomes triple bond, okay, and then this bonding pair is changed to a lone pair, then it becomes a single bond, and you can see the structure like that. You can write. Now, you can see that this structure also correct Lewis dot structure, but they are all called resonance structure or canonical structure or imaginary structure contributing to the actual electronic ground state of N2O. Among these, which is the most contributing structure? How to find out? One can also find out the most contributing structure to the electronic ground state structure based on formal charge. Actual, okay. So, you can also find out how to, okay, which is the, now the question is which is the best structure, or which is the structures which is contributing more to the actual structure. Which can be decided based on as well, okay, from based on formal charges. Let us see that. Then to find out what is the actual structure, then you have to follow certain rules, okay, for to select the best structure, to select structure. To select the best structure, you have to follow the following steps. The structure with formal charge of 0 is preferred. Formal charge. The structure with a formal charge of 0. That means if there are more than one structures, then you have to choose a structure which has no charge. So that means the charge should be equal to 0. So there should be no charge, plus 1, minus 1, like that. There should not be any charges on any of the atom. That structures are preferred structures. So that is the first condition. The second one is you choose a, so if there is no such structures carrying 0 charges, then you have to go for another structure which is carrying the charges which are closer or closest to 0. That I will explain later on. Okay. If there is no structure with 0 formal charge, then you have to go for a structure with formal charges, its value is equal to 0 or closest to 0. That would be the preferred structure. The second condition is that choose negative charge should be on atoms should be on atom of more or most electronegative element. So that would be the next condition for choosing the best structure contributing to the actual structure. Now if you look at these 3 molecules, now we have to find out the formal charge for all of this. When you do a formal charge for all of them, you will find that it is minus 2 here. You can calculate. I am giving the right away writing that formal charges from already I worked out, plus 1, this is plus 1. Now on charge on this one is a plus, it is minus 1, this is a plus 1, this one is a 0, and here you have 0, then here you have okay, the plus 1, here you have minus 1, correct. So this is a minus 2 because in addition to lone pair there are 2 more electrons are on this nitrogen atom, because our nitrogen balance is 3. Okay, so apart from 2 valence electron lying on there, it has 2 more electrons, so it is 2 minus. If you look at this nitrogen, there must be a lone pair of electron lying on the nitrogen atom, then it becomes 0, but the lone pair is bonded here, so it is a plus 1. Okay, then if you look at this one, okay, there must be 2 lone pairs on oxygen atom, on this oxygen atom, but there is only 1 lone pair. The another lone pair is consumed for forming a bond, so that means plus 1 here. That is correct. Now if you look at the same way, it is minus 1 because one electron is acquired by this nitrogen atom. This is plus 1, and then this one is correct because there are 2 lone pairs on this oxygen atom. It's 0. Okay. Now if you look at this one, there is a lone pair on the nitrogen atom, so 3 balance is 3, so it is correct 0. But if you look at this, a lone pair is used for forming a bond, so plus 1. But if you look at that, this oxygen atom carries 1 more lone pair, so it is minus 1. That is correct. Now among these 3 structures, which is the actual structure? Now when you compare the resonance structures for NO3 minus, here it is, all these 3 structures are equally contributing and they are equivalent. All 3 structures are equivalent. Okay. Unlike this, resonance structures for NO2 minus is not equivalent. They are 3 different structures, but which is the actual contributing, are among this which structure is contributing more, that you can decide by following the formal charges. Then you have to look for a structure with the formal charge of 0, but you cannot find any structure with formal charge of 0, because there is a charge here is a +1 -1, here is a +1 -1, here also -2 +1. So, all these structures carry some charges. So, then we cannot decide based on that. Then you go for a okay, relax the rule little bit. So, go for a structure with formal charges equal to 0 or closest to 0. Now, if you look at that, the formal charge on is -2, but here -1 +1, here -1 +1. So, which are closer to 0 compared to this one. So, these two structures we can choose. Among these two structures, okay, so among these two structures, for example, this is A, this is structure B. Among these two structures, which is most contributing structure, that you can decide based on the second rule, that is the negative charge should lie on a atom which is more electronegative. So, if you look at here, the charge on this oxygen atom, okay, between nitrogen and oxygen is more electronegative than nitrogen. So, the formal charge on this oxygen atom is 0. If you come to this structure, the formal charge is -1. So, the negative charge lies on electronegative oxygen atom. So, this structure is most preferred structure. So, structure B is the most preferred structure, is the most preferred structure. Now, in fact, it is found experimentally that it is if you look at the bond distance, okay, NO. So, if you look at the bond distance, bond length between N and atom lies between double bond and single bond. Similarly, if you look at the bond distance or bond length between N and O, it lies between single bond and double bond. So, that those are the facts found experimentally, matches with what we expect based on Lewis dot structure. Now, let us see few more examples. If you take a molecule such as PF5 and then SF6, then you can draw a Lewis dot structure for this, like this, P 5 bonds, like that. Okay, I just drawn approximately structure. Its actual geometry is a trigonal bipyramidal, which I have not written here, because you can draw a Lewis dot structure as such. Now, and then you see that you can put lone pair here, like this. And this, you can also do a calculation. Phosphorus atom belongs to the fifth group elements. It is so number of valence electron is 5, okay, plus 5 into 7, because the valence electron for fluorine atom is 7. So, that is 35 plus 5 equal to 40 valence electrons. Okay. So, now that valence of 40 electron you can find by counting this electrons from here. There are 5 bonding electrons. So, 5 into 2 equal to 10 electrons. There are 3 lone pairs on each fluorine atom. So, 3 into 2 into there are 5. So, 5 equal to 30. So, in total 40 valence electrons. So, the total is matching with that. Now, you see here the terminal atoms, that is the fluorine atoms, attains, each fluorine atom attains the octet of electrons. But if you look at the number of valence electron which is shared with the terminal fluorine atom by phosphorus atom is 10. See that 2, 2, 2, 2, 2. So, it has 10 valence electrons. So, it is more than octet of electrons. That means phosphorus requires more than octet of electrons in this molecule. So, these compounds are called hypervalent compounds. Another example is this one. There also you can write similar structure. you can write. Now, if you look at the number of valence electrons shared by sulfur with the neighboring fluorine atom is 12. So, sulfur has 12 valence electrons. So, it exceeds octet rule. So, these two compounds are called hypervalent compound because the valence is hyped, that is why it is a hypervalent compound. The valence actually, okay, as per the fifth group elements, okay, it should obey the Lewis dot structure or octet rule, but octet rule is not obeyed here. The number of valence is valence electron around this sulfur atom is 12. For this phosphorus compound it's 5, okay, it's a 10. So, the number of valence electrons exceeds octet rule. So, these compounds are called hypervalent compound, and it should not be confused with SO4 2 minus. For this molecule you can write a structure, this is like this, you can write a structure, you can write a structure, this is minus, this is minus, this is 0, okay, formal charge on this is 0. Here it is, if you draw the structure here it is 0. Now, if you count the number of electron around this sulfur atom is, okay, so 1, 2, 3, 4, 5, 6, 6 into 2, 12 valence electron, but it is not okay, hypervalent compound. Okay. So, it is a extended octet rule, okay, extended its octet rule. So, to okay, this structure is drawn such that if you draw a okay, another molecule, so to avoid the higher formal charge you will draw this structure. So, this structure you can draw from here. Now, the formal charge on this sulfur atom is 2 plus, this is minus, okay, and this is minus, this is minus, this is minus. So, the overall charge is okay, 2 plus, this overall charge is 2 plus. So, on this sulfur atom it obeys the octet rule, okay, so because there are 8 electrons around this sulfur atom, but it carries 2 plus charge, higher charges. To avoid that we can write like this type structure, okay. It does not mean that sulfur okay, does not obeying the octet rule. Thank you.